Well, you know, you went during class, you just run laps up and down the stairs. I'm gonna start working on it. Start on the stairs. Didn't work out. Maybe we can do that as possible. No, come back here out of that. I'm like backpedaling. Yeah. Or the gym does like a full body movement. Like you do one muscle group. He does one every time he does full body. He like balances while on the ball, while squatting. And like shoulder press. You don't need to know what the process is.
Okay, good morning everyone. Good morning. We have our final exam coming up next week. Okay, so I want to do something similar to what we did for midterm 2. Did that work for the majority of you? A little longer time period. Okay. So I believe the exam is on December 16th, but I want to open up the exam on December 15th, and it is going to be timed so that people in the regular class, you will have around 4 hours to complete the final exam. Okay, the exam should not take more than 2 hours. That's the typical allotted time for the exam, but I'll be giving you 4 hours for it. Okay, so I'll mention this and also the exam topics and so on. So I'll open up the exam on December 15th. This is going to be on Calvin. December 15th, I'll open it up at 9 a.m. or some same time. And then, according to the university rules, I have to close the exam on December 16th by 6 p.m. I cannot keep it until 11:59. Okay? So this is how it is, and it will be available till 6 p.m. This goes to the entire class. It is not 11:59 p.m. 6 p.m. please. Okay. This will be a timed exam. Do you prefer open book, open notes? Because I can't police anybody's behavior, right? So even if I say close book, close notes, what's going to prevent that from people from looking up things? So I think let's level the playing field. Let's say this is an open book, open notes exam. And if you're using any information, you got to cite it. Cite your sources. If you're saying, okay, I took it from lecture notes, just say I took it from lecture notes. Okay, if you're saying that I found it online, let's say you found it online, you're probably not going to find the answers online for these questions. But let's say you do, you would tell me, because I'll find out. Okay? So this is a timed exam for 4 hours. Total of 4 hours. 4-hour window. And you can choose any block of 4 hours starting from December 15th, 9 a.m. and all the way until December 16th at 6 p.m. So please notice the exam closes at 6 p.m., not at 11:59 p.m. Okay? All right, and then exam topics. I'm thinking 3 to 4 questions total. a question on shear force and bending moment diagrams. And then combine loading on that particular problem. This will be a 2D problem, so this could be the first problem where you draw the shear force bending moment diagram, you find out the area moment of inertia and so on, and then you figure out, okay, what is the state of stress at a certain point on the bottom, or multiple points on the bottom. Depends. Second will be a 3D problem. Right, this will be inclusive of finding out the principal stresses, the maximum shear stress, and so on. So, Mohr circle, which is what we are doing right now. Okay, we'll continue along with this. 3D combined loading, you have to show me the support reactions, how you found them out. Then you draw the two-dimensional view, you mark the state of stress on a volume element. You say that, okay, if I'm approximating a plane state of stress, this becomes the state of stress on the plane. And then you apply Mohr circle to find out the principal stresses, maximum in-plane shear stress, orientation of the elements, and so on. Okay, so I think it's kind of evident that when I say Mohr stress, it has all of these elements included in it. Then there's going to be a problem on generalized strain, which we're going to talk about today. It's fairly straightforward, you'll see that. Using whatever equations that we have, we can find out the principal strains and so on too. Then maximum in-plane shear strain. So this could be a follow-up to whatever I'm asking in the second question. So you would have found out the state of stress at some point. Using that state of stress at that particular point, using certain transformation equations, figure out what the strains are. Okay? So it could be a follow-up from here, or I could just give you a separate plane state of stress, make you draw the Mohr circle and do many things, but I don't want to repeat stuff that is already asked here, so we'll see how best to make it efficient. Then, I want to go back to torsion, statically indeterminate torsion. I want to do that. I want to make sure you never forget it for the rest of your life. Torsion, statically indeterminate. And this about covers everything that you have seen in strength of materials. If you have shear force bending moment diagrams, you know the shear stress and the bending stresses. If you look at torsion, obviously you know shear stress is due to torsion. Combined loading will include normal forces, so you will have normal stresses due to the normal forces as well. This is all strength of materials. The question is, what do you do with all this information? Which is what you'll be seeing in machine elements if you're taking it, or structural mechanics and civil engineering if you're going forward there. Right? Alright, any questions? Or clarification chases?
Is there going to be another review session like we've done in the past?
Yeah, I will plan to have one. I got to say, maybe this, yeah. When is reading day? Thursday and Friday is reading day?
I think this Thursday.
This Thursday, right? I mean, I usually used to have only one. Thursday, Friday makes Saturday, Sunday is also day. Have a long weekend. So mulling the idea of maybe having an in-person review session where I work out some problems like we're doing now. Maybe 1 hour, one hour and 20 minutes or so. I'll record it on video and then post it on whatever, send a link or something, so whoever can come. But if Carbon Zoom is more convenient, is there any preference here? Do you want the review to be held by a Zoom or in person?
Carbon.
Zoom?
Zoom.
Probably 4 people are there. How about I hold it on Zoom and in person at the same time, or like how we used to have our classes before I became a bad person and I started writing on a chalkboard. Would that work? Yeah. Okay, I'll think about the possibilities. Okay, it depends on whether I can get a room, because the rooms might be blocked out. So that's also there. So if in the worst case we are going to have it over Zoom. So be prepared mentally to be meeting on Zoom on Thursday or one of those days. I'll record it, of course, and post it on Cloud. Okay. I'll be posting a practice exam, but please, this is something I want to make a note of. For the final exam, please do not expect your actual exam to be similar to the practice exam in level of difficulty. Final exam is a place where your entire knowledge of the course is to be tested. Okay? It will be a fair exam. You've seen my exams, they are fair, they are nothing out of the ordinary. If you know the material, if you've done the homework problems honestly and truthfully, you should be in a good position to get a really good score on the final exam. It will be a fair exam, but do not expect that you get similar type of questions. Okay? The questions may have a slight twist to it. It is just to make you think a little better. You have an extended amount of time, 4 hours. It is fairly sufficient for the final exam. I will make sure the questions are not very tedious. I will also make sure that you are not doing the same thing in multiple questions. Draw more circle in question 2, draw more circle in question 3, draw more circle in question 4. I don't want to do that. Just one more circle, figure out the information, and move on. Just show me that you know how to construct more circle. That's all I want. Okay? Any last thoughts before we move on?
So, these are the only topics that are being covered on the exam?
Yes, this is sufficient, I think. Yeah. This is good enough for me to come up with an exam paper. Last thoughts is.
Is it safe to assume that for problem A, it's going to be where you're going to give us like a form of a cross section where we have to do everything based on that?
Not a cross section. You'll be given a beam
Yeah.
with distributed loading on it. You have to draw the shear force diagram, bending moment diagram, find out the moment of inertia, then look at a point on the cross section, write the state of stress, write the stress matrix, end of the story. It's going to be long. It's going to be long. Don't be fooled by these topics. They are quite tedious. As you would have seen from your homework, they are quite tedious. I will make sure that you don't need to go through a lot of grunt work, where the numbers will be little nice, clean numbers. But do not expect it to be a cakewalk. It is not going to be a cakewalk, the final exam. This goes for the entire class. It's being recorded for the World Wide Web here. It is not going to be a cakewalk. Trust me on that. Okay? But I am, in my opinion, a very, very fair grader. I will make sure to grade it in all fairness. That much I promised you. Okay. Any last thoughts before we move on? Yes, yes.
For strain, are you know, is it going to be like similar to what we had in midterm 1, or is it going to be more like?
No, this is going to be different, more interesting, as you'll see. Okay. So I'm going to move on. Okay. If you have other questions, you can communicate by email. Last time I started looking at one of the problems. I'm going to draw the cross section from the last time problem, Friday's problem. Okay, I'm drawing the cross section. The point A, which was the point of interest, was on, I think, the left side here. Point A, this is the Z, Y, and the X-axis. And then I had another point, which was point B. I will focus on point A, get it done today, including the strain calculations. For point B, I will post the solutions, okay, because if you know how to do it for point A, it's the same for point B. Okay? We had the following bending moments and forces acting. So Nx was along the x-axis. I believe it was 100 newtons. Then I had a shear force along the positive y direction, so that was 200. Newtons, and then there was a bending moment about the z-axis, negative z, 400 Newton meters. Okay, and then we figured out the following: the radius was given as 20 millimeters. 20 millimeters. We figured out that the normal stress at the point A was due to the normal force only because the point A is sitting on the neutral axis with the bending. In the homework solutions that I posted, I have the first couple of pages, which is a refresher of, okay, at what points will the bending stresses be 0, at what points will the shear stresses be 0 due to transverse shear. So please take a look at it. Homework 10 solutions. I now realize that it's a lot of hard work after I've done the solutions myself. So I do pity you. Hopefully it was worth it. Alright. So I found out that the stress at the point A was only due to the normal force. So sigma xx at the point A, we got this to be 0.08 megapascals. And this was in tension, obviously, because the normal force is acting out. Then the shear stress at the point A due to the Vy force, now xy, was obtained to be the following. I think 2.12 megapascals. And the direction of the shear force, shear stress is pointing up. Okay, so I drew an area element here. Tensile. Now xy at A, this is all the same stuff as the last time, so nothing new so far. Then we took that area element out and we drew it out as a volume element, and then we impressed upon it a plane state of stress by looking at a vantage point, right? I'm going to slide this panel up. If anybody has any questions so far? Then we took the volume element, squished it into a plane state of stress. This is what we ended up getting. So at A, plane state of stress. I'm not going to draw the volume element, just the area element. Okay. So this is what we obtained. X-axis, y-axis. On the x-axis side, I'm going to have the shear stress of 2.12 megapascals pointing up. And then I'm going to have the normal stresses along the x-axis as well, 0.08 megapascals. Likewise, here, okay, and then we said that the right side is always the side of interest. Okay, so this is the side of interest. And then we said, okay, if I have to figure out what the principal stresses and maximum in-plane stresses are, shear stresses are, I have to draw the Mohr circle. So I figured out the center for the Mohr circle. So CA is sigma xx plus sigma yy divided by 2. Comma 0. Sigma yy is 0 there, right? And so this is 0.04 megapascals and 0. Megapascals. And the point A, which you write after comparing it with the sign convention for stresses. Very important, keep in mind the sign convention. Okay, positive tau xy on the side of interest. If this is my x-axis and y-axis, we'll be pointing along the positive y direction. Okay, and then so we wrote this point down as 2.12 and then 0.08. Sigma xx is positive. So this is sigma xx tau xy. Megapascals, and then the radius is.
When you're given a sigma xx and a sigma yy, what is the coordinate, the x coordinate of A? Is it sigma xx?
Still the same thing.
It's still sigma xx?
Absolutely, absolutely,
Okay.
absolutely. This is always the
Because it's the
Yeah.
side of interest you're only looking at?
Correct.
Okay.
Correct. So this is essentially the point A. They are all the same.
Okay.
Very important point. please notice, I am always interested in this particular side, where I have chosen a positive x-axis to be to the right, positive y-axis, okay, hang on a minute. And the coordinate for the point of interest is the stress on this side only, which is sigma xx, and then tau xy. According to the sign convention, this is pointing in the positive direction, this is pointing in the positive direction. Question.
At point B, would it be like the same thing?
Point B is the direct opposite of that. So that's going to be here. They'll both be negative.
But you're gonna post the solution, so we'll see that.
Oh, you mean that point B there?
Yeah.
Oh, okay. There are 2 point B's. There's a point B on the Mohr circle, and then there's a point B on the cross section. But I'll do that for point B as well. So we'll finish this out, and then I'll come to point B. If we have time, I'll do it when I'll post the solutions.
Sounds good.
Okay. I'm going to get to the strains by today. Okay. So we found the radius. Okay, these formulas don't change. It is nothing but the difference between the coordinates of point A and the point C. That's your radius. So that's going to end up being the following. If you do the math, sigma xx minus sigma yy by 2 square, power xy square, the power 1 by 2. I'm taking sigma xx and subtracting it from here, so I'm going to end up with sigma xx minus sigma yy divided by 2, all divided by 2. All to the power 1 by 2. Obviously, you cannot get an imaginary radius, so if something of that sort happens, something's wrong. Okay. These are the 3 things I need to construct the Mohr circle, and we did that last time. Positive sigma, positive tau, the origin is O. Whatever is the units of the problem. Here was the origin. And then I mark the point C, I mark the point A, join them together, that's your radius. Point C suffix A, and then point A suffix A, somewhere here. Using that as a radius, we were able to draw the circle. The circle intersects the sigma and the tau axis at multiple points, obviously. I then draw a vertical line from the top to the bottom passing through the point CA. Okay, so this is the vertical line that passes through. And 2 more points of interest on the left and the right, and my line CA is a reference line. Alright, so let us take a look at the principal stresses. How to get the principal stresses is from the line CA, rotate counterclockwise to the first intersection point on the x-axis, which is the value of sigma 1. This is going to be sigma 1. In this case, it is ending up to be positive. On the other side, the second point of intersection here is sigma 2. It is on the negative sigma axis. This is the negative sigma direction. This is negative tau. From the line CA, rotate counterclockwise. This angle is going to be 2 theta p 1. You can figure out the angle 2 theta p1. We did that last time, so I draw it out. This is the radius. Magnitude of tau xy, depending on whether you have positive or negative, it does not matter when you're calculating the angle. This is 2 theta p1. Okay, and then so sine of 2 theta p1 was tau xy, and the radius. the radius we obtained to be around 2.13 megapascals. Okay, so radius R. And so 2 theta p ended up being approximately 84 degrees. If you do the substitution, tau xy is 2.12, this is 2.13, very, very close to 0.99. Okay, so 2 theta p1. So theta p1 was 42 degrees. And then we said that, okay, sigma 1 and sigma 2 values can be obtained. Sigma 1 is nothing but the radius plus the distance from point O to point CA. So I'll write these things out and then we'll draw the rotated planes. Okay? I'm going to erase this particular panel here. Alright. So sigma 1 and sigma 2 is going to be whatever the distance from O to CA and then the radius. Okay, so this is going to be 0.04 megapascals plus 2.13. So that's 2.17. Sigma 2 is negative, so the first thing you do is put a negative sign. It is negative because of the fact that it is intersecting on the negative x direction, or the negative sigma direction. That's the reason. This is negative. It's going to be the radius minus 2.04. So many megapascals. Okay. Once I have everything, then I have to draw the orientation of the principal stresses, the principal planes, and so on. So here is what I do. First step. X-axis, y-axis. This is what we had drawn previously. From the x-axis, you always start from the x-axis because you're using the point A as the state of stress on the side that contains the positive x-axis. Rotate by this amount, 2 theta p1. If it is counterclockwise, rotate counterclockwise. It is possible that perhaps the state of stress at A might end up lying here for a different problem. Okay, so I would still go counterclockwise, but by a larger amount, more than 90 degrees. So here I have the one direction, which is rotated by 42 degrees, theta p1. The two direction is going to be perpendicular to the one. Principal planes are free of shear stress, so if I draw the state of stress on the principal plane, and I'm going to get rid of this particular panel here. Then here is what we end up getting. I'm going to draw a rectangle that is rotated by 42 degrees with respect to the original one. Two direction. Is everybody understanding what we're doing so far? Same stuff as last time. Okay, I'm just repeating information, but I want to be on the same page. Along the one direction, sigma 1, positive, so 2.17. Along the two direction, sigma 2 is negative for me, which means that it's going to be compressive. Okay, so it's going to be pointing sigma 2, sigma 2, and if you want, you can also mark the angle between the 1 and the x-axis. Degrees, and this is where we stopped last time. Okay, and now I want to draw the same thing for the shear stress, the shear plane. And I want to see if there are any questions so far. Yes, sir.
Whenever you figure out your reference line, will it always be the case where sigma 1 will be towards the positive side of the axis and C2 be towards the negative side?
Not necessary. It is possible that my center can be a negative value because both sigma xx and sigma yy can both be negative. So this could be far shifted on there, and then my line could be from there all the way to somewhere else. And so if I draw a circle, it will be completely on the left side. It depends on the state of stress. So maybe for Wednesday I'll pick a problem of that type, and then we'll walk through it. Yeah, it's a good idea. Okay. All right. Now to go to the shear plane. Once again from the line CA, go all the way to the first shear value that you see. Okay, so this is the first shear value that you see. This is the maximum shear stress value in plane shear stress. So if I mark it out, this is going to be minus tau max in plane. Why is it minus? Because it is on the negative tau axis. The one on the bottom is going to be the positive tau direction, so it's right here. It is quite easy to see that the maximum in-plane shear stress value is nothing but the radius of the Mohr circle. So I can directly write it out. The tau max in plane is equal to the radius, which is 2.13 megapascals. And it is also important to understand that at that particular point where the shear plane exists, there is going to be an average normal stress on all the faces. Okay, so that's going to be sigma average on the shear plane, which is nothing but the distance from point O to point CA. So this is sigma xx, sigma yy by 2, which is 0.04 megapascals. Positive. Okay, sigma xx was positive for us, 0.08. Sigma yy was 0. So the sum of these two ended up being positive. Now, important question is this positive or negative? So watch this. First of all, starting from the reference line, I am going all the way to the point where I first encounter the maximum in-plane shear force, shear stress. So that angle is going to be 2 theta S1, which is nothing but 90 degrees plus 2 theta P1. Right? You all see that. Okay, so in this case I can say that 2 theta S1 is 90 degrees plus 2 theta P1, which means that theta S1 is 42 plus 45 degrees. Okay, so I'm going to erase this panel here. So that theta S1 for us is going to be 45 plus 42, or 87 degrees. Until this point, are there any questions? Line of reference is always a line CA. No matter where it is, it's where you're going to start. As you're measuring the angles, you're always going counterclockwise. No matter what anybody says. No matter even what the book says. Okay? Now, I want to draw the state of stress on that plane, and here is how you do it. First step is you mark the x and y directions. The first shear direction, which is x suffix s, is at an angle of 87 degrees with